In this video, we will look at the nearest neighbor algorithm. In our last video, we were considering the traveling salesman problem, or TSPs, as a means of brute force to find an answer. And that would be to literally list out every single possible route, which is overwhelming when we have a high number of vertices. Even computers will struggle this if the number of vertices is very high at all. So we're going to turn to a different type of algorithm, an heuristic algorithm, which is an efficient algorithm, meaning it's fast to find the route, but it only gives an approximate solution. Okay, so it doesn't give necessarily the best one, which we call optimal. So here is one of those algorithms. We're going to look at 3 different ones, 2 this week and 1 next week. The first one is called the nearest neighbor algorithm. And here's what we're going to do. Just choose a starting point. Just pick a point. All right, then move to the nearest unvisited vertex. Right, so from wherever you're standing, right, there you are. What's the cheapest route? Of all the routes that you could leave from there, you're going to go down the path that is the cheapest. All right. Now, you're going to continue doing that process. That's part 3, right? Repeat until the circuit is complete. Now, remember, you're always visiting unvisited vertices. You're not going to go back to a place you've already visited until you're ready to go back home. So that's a key. Let's take a look at our first graph. All right, so here we have a connected, complete graph of A, B, C, D. And I want to find the cheapest, right, or the smallest. I don't know what these numbers represent. So I just pick a starting spot. Maybe I'm like, I don't know. I'll just start at C. Here we go. All right, so C. So this would be my nearest neighbor algorithm circuit. All right, I'm going to show you how to do it. You pick a point, start at C, and then I just choose the cheapest route. Well, there are 3 routes out, right? You can go down that route, or that route. And the weights are 8, 18, and 22. And all you do is choose the cheapest one. And the cheapest one of those 3, of course, is 8. Right? So I'm going to start here. I'm going to first travel down 8 to D. So that's the first part. Start at C, go to D. All right. Now that I'm at D, I don't have 3 choices. I only have 2 choices, right? I can either keep heading to A, or I can head to B. I can't go back home until I've traveled. So which one of those 2 options is the cheapest? Well, one is 12 and one is 10. Of course, the 10 is cheaper, so we'll choose the 10, right? We'll then head across here to B. Great. Now that I'm at B, I actually only have 1 choice. It looks like there might be 2 choices. I can either go to A or C, but remember, I can't go back home, right, where I started until I've traveled everywhere. So my last choice, I have to go to A because I haven't visited that yet. You can see that's a very heavy weight. Now I've been everywhere, but remember, this is a traveling salesman and I'm doing a circuit. I always have to come back home. So lastly, I'd have to come right across to the middle and I would be back at C. Well, let's think about the weight of what I just outlined, right? The weight would be starting at C, going to D, 8 plus 10 plus 38 plus 18. Grand total. Let's take a look at that. 8 plus 8, 10 plus 38 plus 18. 74. Do you think that's the best possible route? It may not be. In fact, we probably feel using that 38 that it's certainly not the best route. So that lets us know that, wow, this is an algorithm, but it doesn't necessarily give us the best result. It just gives us a result. Sometimes actually it will give us the best result. Many times it will not. So we're going to look at ways to improve it in a future video. All right. So what we say is that the nearest neighbor algorithm, we call that a greedy algorithm. It only looks at the immediate decision, like what is the cheapest route from where I'm standing, but it doesn't consider the consequences in the future. And that problem we just did, a consequence of the future is that we had no choice but to use a weight of 38, and that made us have a very heavy weight, the final end. Let me show you one more example using a mileage chart. Darren is a sales rep whose territory consists of the 6 cities shown in the mileage chart. Darren wants to visit customers, I have a little typo there, customers at each of the cities, starting and ending his trip in his home city of Atlanta. So we're going to start in Atlanta. His traveling costs, gas, insurance, etc., average 75 cents a mile. So we don't really need to use that. I'm not going to calculate the final amount of the trip, although I could. I'm just going to know that the more I travel in miles, the more expensive that it is. So one way to do this, and I like to do this, is to take the mileage chart, but think about it as a map. Now, you could look at a map of the United States and you could kind of place these cities accurately where they are. But when you do graph theory, you can actually just do it abstractly. It doesn't really matter that it looks like the actual map. So I'm going to do Atlanta, Columbus. I'm going to do Kansas City. All right. I'm going to do Minneapolis. I'm just going around in order. Pierre, and Tulsa. All right, those are my 6 cities. And it's a complete graph. So in other words, you can go from any city to any city. You can go down any of these paths. It's fully connected. All right. Not only like that, but each city will be connected. So there will be lots and lots of connections. I hope I don't miss one, right? I might find one in a little bit. And what you should find out in the very end is that each route has 5 connections. I see one more right there. Each route has 5 connections because there are a total of 6 cities. It looks like I have them all now. Now, I probably don't want to, well, actually, I see one more. There's one right there. All right, now I think I have it. You probably don't want to list all possible routes. Of course not. That would take who knows how much time. Computer could do it quickly, but by hand, it would take a long time. So we're just going to use the nearest neighbor approach. The nearest neighbor approach is to pick a starting place. Well, Darren lives in Atlanta, so we're going to start there, right? Atlanta. I'm going to use A for Atlanta. And then where does he go next? He goes to the cheapest place. Now, he does have options. He can go to Tulsa, Pierre, Minnesota, Minneapolis, Kansas City, or Columbus. But what we're going to do is look at the chart. So what I would do is look at the first line, Atlanta, and look at the numbers, right? Look at the values of traveling to the other cities. Those are the costs. Notice that it's a repeat here, right? It's a repeat if you look down that direction. You can look either direction you want. I'm just going to look across the top. Which one of those numbers is the cheapest? The very first one is Columbus. So we choose that. Now, remember, what we don't know is will this damage us in the future? So I'm going to erase this and kind of draw only my actual route on the map. All right, so I choose first. Okay, let's go from Atlanta to Columbus. All right, and I go along that route. And so I'm going to write my circuit out, Atlanta, Columbus. All right, now I'm at Columbus. All right, so now I'm looking at the second line. Now what's the cheapest place to go to? Well, the actual cheapest number in this line is Atlanta, but I can't go back to Atlanta, right? So I have to go to a new place. So the next cheapest one is Kansas City. You can see that right here at $6.56. So once I'm at Columbus, I'm going to go to Kansas City. And that will be that much money. Now I'm living at Kansas City. All right, I'm going to look at this third line. And where can I go? I can only go to Minneapolis, Pierre, or Tulsa. These last 3. Of those 3 choices, and again, I can't go to the first 2 because I've already visited those. Of these last 3, which one's the cheapest? And Tulsa is at $248. So then that's where I'll go next. I'll go to Tulsa. All right, so I'm going to travel over there. Right now, I only have 2 choices left. I can go to Pierre or to Minneapolis. So I'm at Tulsa currently, right? So I'm down here at this bottom. Notice I jumped in the table. And which one is my cheapest? Well, I can only go to 2 places, either Pierre or Minneapolis. That's the only 2 places I haven't visited yet. Which one's the cheapest of those 2? Minneapolis is the cheapest. So I go there, $695. All right, Minneapolis. And then lastly, let me update my map, right? I've actually gone to every city. That's why the picture is really helpful. I've gone to every city except one. I have no choice but to go to Pierre. So I'm just going to say, okay, I have to go from Minneapolis to Pierre. So that forces me to go and choose this number here, which doesn't seem too bad at $394. Now that I've visited every city, remember, it's a circuit. So you must go back home. I have to go from Pierre all the way back. Well, I could have used my highlighter, but from Pierre back to Atlanta. And so that also is a cost on the map. All right. Pierre back to Atlanta. I'm going to end with an A, and I can find that on my map here. It's, not good, $1,361. So Darren's total cost could be found by looking at all of the miles that he went from Atlanta and so on, right? Around. So 533, let me scribble that out. That's a dollar sign. 533 plus 656 plus 248 plus 394. I'm just going line by line on the chart. 1361 plus 695. That would be his total mileage. And we could figure out the cost of that by taking this mileage and multiplying it by 75 cents per mile. All right. Now, the issue is I have no idea, none, whether this is actually the cheapest route. It might not be, but at least it gave me a route and I had a method for getting there, and it was an efficient algorithm. But keep in mind that this is a greedy algorithm. So we're going to revisit this problem in a future video to see if we might find a better result than that.